Welcome students to MOOC's series of lectures on advanced probability theory. This is lecture number 26. So, if you remember, we are working on convergence of random variables, and we have discussed two major types: convergence in distribution when a sequence of random variables x n converges to another random variable x, and also convergence in probability and we denote that as a sequence of random variable x n converging to another random variable x. We have stated that convergence in probability is a stronger statement than convergence in distribution. Why? Because there may be situation when a sequence of random variables x n converges in distribution to x, but not in probability. On the other hand, if x n converges in probability to x, then x n also converges in distribution to x. So, let us prove the result. So, theorem: if x n converges in P in probability to x, then x n converges in distribution to x. Proof: consider the event x n less than equal to x. Now, we can write it as x n less than equal to x is equal to union of two disjoint events x n less than equal to x and x is greater than equal to x plus epsilon union x n less than equal to x and x less than x plus epsilon, where epsilon greater than 0. That is, it is a small quantity. Note that the above event is contained in the following. That is, this is contained in x less than x plus epsilon union x n less than equal to x and x greater than equal to x plus epsilon. Why? Because I am keeping the same event here, these two are same, but this is a super event of this one, as we have deleted this condition. Therefore, probability x n less than equal to x is less than equal to probability x less than equal to small x plus epsilon plus probability x n less than equal to x intersected with x greater than equal to x plus epsilon. Therefore, if f n denotes the cumulative distribution function of x n, then we can write f n x is less than equal to f at x plus epsilon plus probability x n less than equal to x intersected with x greater than equal to x plus epsilon, where f is the cumulative distribution function of x. Now, this is less than equal to f x plus epsilon plus probability modulus of x n minus x is greater than equal to epsilon. How? Since from this event we can see that x n less than equal to x and x is capital X is greater than equal to x plus epsilon. Therefore, together they imply that the distance between x n and x is at least epsilon. And since this can happen in some other ways also, therefore, this event is contained in this event and therefore, this probability is bigger than this probability. In a similar way, f at small x minus epsilon is equal to probability x less than equal to x minus epsilon is equal to probability x less than equal to small x minus epsilon and x n is greater than x union with x less than equal to small x minus epsilon intersected with x n less than equal to x. So, again I have divided this event as a union of two different disjoint events. Less than equal to probability modulus of x n minus x greater than equal to epsilon. Again by a similar logic, x n is greater than x, but x is smaller than x minus epsilon. Therefore, the distance between them is greater than equal to epsilon, plus this whole event is contained in x n less than equal to x. Therefore, we are writing there f n x. Therefore, f at x minus epsilon minus probability modulus of x n minus x greater than equal to epsilon is less than equal to f n x. Also, we have found if we go back, we have found that f n x is less than equal to this entire quantity. Therefore, we can write it as that f n x is less than equal to f at x plus epsilon plus probability modulus of x n minus x greater than equal to epsilon greater than equal to epsilon. So, together we write f at x minus epsilon minus probability modulus of x n minus x greater than equal to epsilon less than equal to f n x less than equal to f at x plus epsilon plus probability modulus of x n minus x greater than epsilon. Now, it is given that x n converges in probability to x. This implies probability modulus of x n minus x greater than equal to epsilon converges to 0 as n goes to infinity. That is, therefore, for sufficiently large n, we can say that f at x minus epsilon less than equal to f n x less than equal to f x plus epsilon. Why? Because this term is going to 0 and similarly this term is also going to 0. This is true for any epsilon greater than 0, however small it is. Since x is a point of continuity, for f x, we can say that f n x converges to f x. Therefore, this sequence of random variables x n converges in distribution to x. Therefore, since convergence in P in probability implies convergence in distribution, we say convergence in probability is a stronger statement than convergence in distribution. Question is, does there exist any condition such that convergence in distribution implies convergence in probability? The answer is yes, and here is the theorem. If x n is a sequence of random variables such that x n converges in distribution to a constant k, then x n converges in probability to k. That is, here we are looking at a degenerate case. X n is a distribution which is converging to a constant k in distribution, then x n converges in probability to k as well. So, let me first give you an example. Suppose consider x n to be distributed as follows. It takes the value k minus 1 by n with probability half and k plus 1 by n with probability half. Therefore, and let f n be the corresponding cumulative distribution function, then as n goes to infinity, the CDFs look as follows. Therefore, its CDFs will look as follows. Suppose this is k, this is k minus 1 and this is k plus 1. Therefore, x 1 will have a CDF which is 0 till k minus 1. At k minus 1 it jumps to half and then it continues till k plus 1 with half, then it jumps to 1 at k plus half and continues like that. So, that is the CDF of x 1. X 2 will take the values k minus half and k plus half with probabilities half and half. Therefore, its CDF will be 0 till k minus half. It is going to be half at k minus half and it is going to be 1 at k plus half. Therefore, this is the shape of f2. Therefore, what is going to be the CDF of say k minus 1 upon n when n is large? So, let us call this value k minus 1 upon n and this value to be k plus 1 upon n, then its CDF will look like this. It is 0 till k minus 1 upon n, half at k minus 1 upon n. It will continue like this till the point k plus 1 upon n, then it will make a jump to 1 and continue at 1 throughout. Therefore, what is happening? We can understand that as n increases, we are getting a smaller and smaller intervals around k where the actual jump is occurring. Therefore, this by taking n to be very large, we come to the interval k minus epsilon to k plus epsilon. If this is clear, then let us proceed as follows. We need to show that probability modulus of x n minus k greater than epsilon is goes to 0 as n goes to infinity, where epsilon is a small positive number. So, proof: we have x n converges in distribution to k. Therefore, for any delta greater than 0, f n k minus delta goes to 0 as n goes to infinity, and f n k plus delta goes to 1 as n goes to infinity. To show x n converges in probability to k, that is probability modulus of x n minus k less than epsilon goes to 1. Since f n k minus delta converges to 0, therefore, there exists n 1 such that for all n greater than equal to n 1, modulus of f n k minus delta is less than epsilon by 2. Also, f n k plus delta goes to 1, therefore, there exists n 2 such that for all n greater than equal to n 2, modulus of f n k plus delta minus 1 is less than epsilon by 2. Choose n to be maximum of n 1 and n 2. Therefore, for all n greater than equal to n, let us put bound on f n k plus delta minus Fn k minus delta. Since modulus of Fn k minus delta less than equal to epsilon by 2, therefore, minus epsilon by 2 less than equal to minus Fn k minus delta less than equal to epsilon by 2. Also, modulus of Fn k plus delta minus 1 less than equal to epsilon by 2. Therefore, 1 minus epsilon by 2 less than equal to Fn k plus delta less than equal to 1 plus epsilon by 2. Therefore, by adding for all n greater than equal to n, 1 minus epsilon less than equal to Fn k plus delta minus Fn k minus delta less than equal to 1 plus epsilon. Since this is true for any arbitrary delta, however small it is, we conclude that Fn converges in probability to F, which is the CDF of variable x, defined as it takes the value k with probability 1. So, that proves the result. Let me now give you an example of convergence in probability. Let x 1, x 2, x n be independent random variables such that each x I is distributed as uniform minus 1 comma 1. Consider the sequence of random variables y 1, y 2, y 3 like that, such that y I is equal to maximum of x 1, x 2, x I for all I is equal to 1, 2, 3 up to infinity. Show that y n converges in probability to 1. So, solution: let epsilon be greater than 0, then probability modulus of y n minus 1 greater than equal to epsilon is equal to probability y n greater than equal to 1 plus epsilon plus probability y n less than equal to 1 minus epsilon is equal to probability maximum of x 1, x 2, x n greater than equal to 1 plus epsilon plus probability maximum of x 1, x 2, x n is less than equal to 1 minus epsilon. Since x i's are uniform over minus 1 to plus 1, therefore, probability maximum of x 1, x 2, etc. greater than equal to 1 plus epsilon is equal to 0, because the upper limit of the value that the random variables can take is only 1. Therefore, probability modulus of y n minus 1 greater than equal to epsilon boils down to probability maximum of x 1, x 2, x n is less than equal to 1 minus epsilon. Now, probability maximum of x 1, x 2, x n less than equal to 1 minus epsilon is equal to probability x 1 less than equal to 1 minus epsilon, x 2 less than equal to 1 minus epsilon, x n less than equal to 1 minus epsilon is equal to probability x 1 less than equal to 1 minus epsilon, this whole to the power n, since x 1, x 2 are independent. Now, x 1 is uniform in minus 1 to 1. Therefore, probability x 1 less than equal to x is equal to x minus minus 1 upon 1 minus minus 1 is equal to x plus 1 upon 2. Therefore, probability x 1 less than equal to 1 minus epsilon is equal to 1 minus epsilon plus 1 divided by 2 is equal to 1 minus epsilon by 2. Therefore, probability x 1 less than equal to 1 minus epsilon whole to the power n is equal to 1 minus epsilon by 2 whole to the power n. Now, epsilon is greater than 0, therefore, 1 minus epsilon by 2 is strictly less than 1. Therefore, probability modulus of y n minus 1 greater than equal to epsilon, which is equal to 1 minus epsilon by 2 whole to the power n, converges to 0 as n goes to infinity. Therefore, y n converges in probability to 1. And since y n converges in probability to 1, implies that y n converges in distribution also to the constant 1. Okay, friends, let me now talk about another mode of convergence, which is called almost sure convergence. Definition: let x n be a sequence of random variables x n is said to converge almost surely to a random variable x if and only if probability of omega such that x n omega converges to x omega is equal to 1, and this is written as x n almost surely converging to x. Note that all x n's and x are defined over the same probability space omega s p, and small omega belongs to capital omega. Therefore, what almost surely convergence means that this set of points A of small omega, A contained in capital omega, is such that probability of A is equal to 1. So, let us recall the following. Let x and y be two random variables defined on 0 cross 1, 0 to 1 cross 0 to 1. That is, we are looking at points belonging to unit square. We have discussed that the probability x is equal to y is 0, because the event x is equal to y means the points are chosen from this diagonal, and since the measure of the diagonal OP say is 0. Therefore, consider now a sequence of random variables x n defined as follows. X n is defined from 0 1 cross 0 1 such that this takes the value 1 if x is not equal to y and 0 if x is equal to y. Consider x to be defined on the same omega such that x is equal to 1 for all x comma y such that 0 less than equal to x, y less than equal to 1. Therefore, we notice that x n's are different from x, but this set of points on which x n is equal to x is equal to all those omega belonging to 0 1 cross 0 1 such that x not equal to y. So, if we call it A, then probability of A is equal to 1. Therefore, x n converges almost surely to the random variable x, which takes value 1 throughout the entire unit square. Another example, consider some probability space omega s p such that x n omega is equal to 2 plus 1 by n. Therefore, probability of omega such that x n omega converges to 2 is equal to probability of omega is equal to 1. Since for all omega belonging to capital Omega, x n omega converges to 2, since 1 by n converges to 0. Therefore, x n omega almost surely converges to the constant 2. Now, the concept of almost sure convergence needs more understanding of the measure theory. Sometimes it is counterintuitive Say for example, consider the set of real numbers say greater than equal to 0, that is all positive real numbers. Now, real numbers are of two types. Rational and irrational. we all know that there are countably many rational numbers. However, the measure of the set of rational numbers is 0, although there are infinitely many rational numbers. To understand this concept, one needs to study deeper level of mathematics. Hence, I am not going much into the detail. So, I conclude the talk with the following information that almost sure convergence is a stronger condition than convergence in probability. That is, if x n converges almost surely to x, then x n convergence in probability to x, but not vice versa. We can find examples to show that x n converges in probability to x does not imply x n converges almost surely to x. I want you to remember this fact, because we shall need almost sure convergence when we study strong law of large numbers in subsequent lectures. Therefore, we conclude that x n almost surely converging to x implies x n converging in probability to x, which implies x n converging in distribution to x. So, with that message, I stop here today. From the next class, I shall start with laws of large numbers. Okay, then, thank you.